This conference will now be recorded.
So, very good evening, Deepa. You have also come today. Very nice. So, today we'll be discussing one important property of liquid or fluid, that is viscosity. So, we'll try to learn what is viscosity, coefficient of viscosity, Poiseuille's formula, Stokes law, and terminal velocity. As far as possible, we'll try to complete this topic today. Okay, so let us see how much we can complete. Okay, so first of all, what is viscosity? Viscosity, if I write a definition, viscosity can be defined as the property or a property of fluid by virtue of which an internal force of friction. Oh, so here should be internal force of friction. So internal force of friction comes into play when a fluid is in motion, and this frictional force tries to oppose the relative motion between the layers. I'll give you certain example, and let me discuss this thing little bit. What is viscosity? See, if you remember, we have learned uh, about friction, right? You have a block of mass like this, and now suppose this is a floor. Okay, this is a floor. It has certain coefficient of friction, static friction. If you apply a force, this is a block of mass m, suppose. Apply a force, then there will be a frictional force at the interface or at the contact surface at this place. Okay, there will be a frictional force arising, and that frictional force generally acts against this applied force. That means in this way, and the force acts tangentially or parallel to the contact surface. Parallel to the contact surface, it arises in between the or at the contact surface. So this is frictional force. Okay, so this is in case of solid. This floor is also solid, and this mass of block is also like a block of mass m is also a solid. So we have learned already friction for solid. Friction for solid surfaces, right? Solid surfaces. Now here we'll be learning friction for liquid surfaces or liquid layers. Okay, or sometime you can, yeah. So this is the friction within the layers of the liquid, within the layers of liquid. So first of all, let me tell you, when a liquid is flowing through a tube, okay, or let me take only one surface, solid. So suppose there is a horizontal fixed surface over which kind of a canal you can think, or river. So when the water flowing, this is the direction of flow, suppose water or any liquid flowing, it will actually flow making some layers, parallel layers. Layers are parallel to the fixed surface or horizontal surface. This is the suppose fixed surface, fixed surface. Okay, so they will make certain layers, and those layers will flow in the direction of flow. Okay, these are the layers of liquid or fluid. Here we are talking about water, layers of liquid. These are layers of liquid. When a fluid or liquid flows, it flow in terms of different layers. Okay, different layers. One layer of water, this one, another layer is this one, another layer is this one, and this one, like that. So different layers, they flow in terms of different layers. Now see, these layers, they have certain surface area. Okay, surface, and when they move, when the water or the fluid is in motion, what happens? What what about now, madam? Am I audible to you? Am I audible to you now? Can you respond through message? Okay, fine. Actually, there is a power cut. I have joined again through my mobile. I don't know how the connection will be. If if the sound is very nice, then it is all right. So we are discussing about viscosity of fluid or liquids. So we know the frictional force for, like, frictional force arising between two solid surfaces. But now we are learning that even in between the layers there is a frictional force. Layers of fluid, in between the layers of fluid there is a frictional force. Okay, so that is what. So viscosity is a property of fluid by virtue of which an internal force of friction comes into play when a fluid is in motion. When fluid is in motion, then the fluids actually move in terms of different layers, and different layers will actually oppose each other's motion, relative motion. Different layers, because of this viscosity, they will oppose the motion, relative motion between them. Okay, I'll just uh, let me. Okay, so this is a, see, look this. We'll we'll discuss the cause of viscosity now. Suppose this is the fixed horizontal surface. Okay, this is fixed surface. Now this is the different. These are the different layers. Okay, these are different layers. Layers of fluid. Okay, different layers of fluid. Now the horizontal surface is fixed, so the layer which is exactly touching touching the fixed surface, that layer does not have any velocity, that is v0, that does not have any velocity. Okay, because that is just touching the fixed surface. Now as you go in the upward direction, the velocity of each layers will be increasing. Look, this layer, so this is the supposed velocity, this is v1. Then in the next layer, see, as you go away from this fixed surface, because here the speed is 0 for the layer which is in contact with this fixed surface. Now as you go upper and upper from, or away from, as much away you go, the speed of the layer of liquid will increase. As you see, this much is the liquid speed of this layer. Then in this speed increases. Suppose this is something v2, again this is v3, v4, this is v5, and among all these layers this has maximum velocity, right? This layer, the topmost layer, has maximum velocity. This has maximum velocity. Okay, this topmost layer. So what is the understanding over here, or what is the knowledge? The knowledge is that the velocities or the speeds of different layers are different. That is the knowledge here. Okay, so what we have understood, that the different layers have different speed. Okay, if you are very much away from the fixed surface, you have maximum speed, and others have velocities or the speeds accordingly. Okay, that means, see, they have relative velocity. So what I wanted to mean is that, see, now this fixed surface, the layer attached with the fixed surface has some velocity v0, it has v1, this has v2, this has v3, this has v4, and this is v5. So if I take any two layers, suppose A and B, suppose this is A and this is B, so A has velocity v2 and this is v3. So you look, there is a relative velocity v relative vr is v3 minus v2. So this is the relative velocity between these two layers. But viscosity, what viscosity does, suppose this layer, it will try to drag this, so this slow moving layer A. So you look, that B is fast moving layer, B layer is fast moving layer, fast moving layer, A is slow moving layer. So what this fast moving layer does, it will try to drag this slow moving layer with its own speed. Okay, so that there will be no relative velocity between A and B. At the same time, what this slow moving layer will do, slow moving layer will try to drag this fast moving layer such that the speed becomes same as A, and there will be no relative velocity. I hope you are understanding. So A and B, they have different velocities or speeds. So each of them will try to drag them along with them such that they will not have any relative velocity between them. So that is what is being stated over here in this statement, or in the definition. So it is internal force of friction. Internal force of friction comes into play when the fluid is in motion. When the fluid is stagnant, there will be no viscosity. There will be no viscosity. If there is no relative velocity, then there is no viscosity. Okay, when only when there is relative velocity, there will be viscosity. Okay, the fluid is in motion. The frictional force tries to oppose the relative motion between the layers. So this is what about. So this is the cause of the viscosity. What is the cause of viscosity? The cause of viscosity is the relative velocity. So the relative speed between the layers, between the layers. So this is the cause of viscosity. Okay, and because of that, viscous drag. So this is called viscous drag. Okay, viscous drag. Okay, viscous drag, and this force acts tangentially on the layers. Okay, tangentially means suppose this is a layer. Okay, it will act in the opposite direction of the motion. This is the motion. This is the viscous force which is acting parallel to the layer or tangential to the layer and opposite to the motion of the flow. Okay, so this is viscous force. Okay, this is viscous force that always acts tangential to the surface of liquid, and it is opposite to the direction of the motion of the fluid. So this is about viscosity. Now we'll learn many other important things about this viscosity. So let me clean this portion. So we'll just now take up few examples where we see viscosities. Like, see, when we swim in water, what we see? When we try to move faster while swimming, we feel some resistance, right? We cannot, like sometimes we cannot move, and that's why you need a practice. And see, when we go for swimming, you have to see the liquid nature of the liquid also in which you are swimming. So why is that resistance appearing? That is due to viscosity. So when we swim in water, we feel some resistance against our motion, and that is offered by the layers of the liquid, that is due to viscosity. So this is one point. See, the raindrops, they also fall very slowly. Why is it so? They are freely falling body, but still their speed is much lesser than what is expected. Why? Because of viscosity of the air. Different layers of air between them. See, in case of air, due to diffusion of various diffusion of molecules produces this viscosity, and because of viscosity, when raindrops falling through the air, the speed is dragged or it is reduced. Now see, if you take in a bottle, if you take some amount of honey, okay, and pour in a beaker using a funnel, what you see that if you simply take water will actually fall through the hole of the funnel, this hole of the this very quickly. Okay, but if you take honey actually doesn't fall very fast. It actually literally trickle downs and trickle downs drop by drop. Okay, if you take honey falls drop by drop. Okay, so those liquids which have or fluids which have especially liquid if you take those liquids which have greater viscosity, they form drops, or it is very what to say, very difficult to pour from one container to another container. It will take long time. You must be aware of things like that. Okay, okay, so this is another point where you see viscosity, the effect of viscosity. And see, another point is, you might have seen in your chemistry lab when we stir something in a beaker, some liquid in a beaker, what it does, it actually rotates coaxially with the beaker. But if we stop stirring with the glass rod, then after some time we see that the liquid stops rotating. Why is it happening? It is happening because there is viscosity, there is internal frictional force. Okay, internal frictional force or internal force of friction that comes into play, and that will stop the motion of the liquid. So these are the few examples of viscosities. Okay, now we'll learn there is something called coefficient of viscosity. Coefficient of viscosity. So to calculate coefficient of viscosity, so coefficient of viscosity is denoted by eta. To calculate the coefficient of viscosity, let us suppose a liquid is flowing in this direction. As you see, liquid is flowing in different layers. Okay, like that, in different layers. Now I am taking two representative layers out of all the layers. What are those? One layer is Q, another one is P. See, as you know, the layer which is in contact with the fixed surface doesn't have any velocity, that we have learnt, and then slowly velocity increases as you go away from the fixed surface. So I'm just considering two layers Q and P. This P layer is at x distance from the fixed surface, and the Q layer is at x plus dx distance away from the fixed surface. And suppose the P layer is moving with velocity v, and Q layer is moving with velocity v plus dv. As we have discussed, the velocity will be more and more if you go away, more and more away from the fixed surface. So it is away from fixed surface. That's why the velocity is more for the Q layer. And each of them has a area A. Both of them has area A. That we are assuming. And as you see, this is the frictional force. It will be acting in between the layers, okay, and it is acting opposite direction to the direction of speed of the layer or direction of flow. All right, now see here the what is the change in the velocity with distance. See, change in the velocity with distance is dv dx. This is called velocity gradient. Sorry, velocity gradient. What is this called? This is called velocity gradient. So velocity, change in the velocity with distance is called velocity gradient. So this is the velocity gradient of the liquid. Okay. So this is actually the rate of change. You can say the rate of change of velocity with distance in the direction of increasing distance. So this is the rate of change. Rate of change of velocity. Rate of change of velocity with distance and in the direction of increasing x or increasing distance. That means this gradient is along this way. Okay, this dv dx. Okay, this is the rate of change of velocity with distance, and that is in the direction of increasing distance. Okay, this is velocity gradient. Now according to Newton has given some idea or some knowledge about this viscosity also. So according to Newton, what we are learning, according to Newton, this viscous force acting tangentially between the layers, and the viscous force will be directly proportional to the area of cross section or area of layers in contact. And this is one point, and second point is that it is directly proportional to the velocity gradient dv dx. Okay, dv dx, it is directly proportional to the velocity gradient between the two layers. Okay, now if we just combine these two proportionalities, then see, I'll just remove this portion. Okay, so look, if we combine these two, what you get, f is directly proportional to a into dv dx. And if we bring a proportionality constant, then we should write this eta a dv dx. Okay, so this is actually the viscous force according to Newton. And see here, this constant, proportionality constant, this is called coefficient of viscosity. Coefficient of viscosity. You might be thinking that is fine, but why is this minus? See, this minus because the viscous force is is in the direction opposite to the direction of the motion of the liquid. Okay, this minus sign is indicating that the viscous force is in the opposite direction of the velocity. That's why velocity or the flow of the fluid or liquid. So that's why this minus sign comes here. Okay, so what we get, according to Newton, the viscous force is directly proportional to the contact area of the or surface area of the contact surface, and force of friction between the layers is directly proportional to the velocity gradient. If we combine this both proportionality, we get this. And now if we want to write in terms of equation, we have to bring a proportionality constant, and that is eta over here along with the minus sign. So this minus sign is actually indicating that the force, this viscous drag is in the opposite direction of the flow of the motion of liquid. And here this eta is called coefficient of viscosity. This eta is called coefficient of viscosity. And see, this coefficient of viscosity actually gives you the nature of the viscosity, the strength of the viscosity. Okay, just by knowing this, we can guess about the liquid or the fluid. So we'll see this
No sound, Ram.
okay, so yeah, I think, am I audible now?
Yes.
Okay, I'll continue. I don't know. In between it is going. I don't know. Maybe because I have joined through mobile. This network is slow bit, but I have. Okay, anyway, I have enough data, something like 1 GB, but still there is some problem. Anyway, so yeah, so I'll continue from this point that coefficient of viscosity. So this coefficient of viscosity is the measure of the amount of viscosity or the nature of the viscosity. So this viscosity actually will coefficient of viscosity depends on the nature of the liquid. It gives a measure of viscosity. Okay, it gives a measure of viscosity. Now see, we have got F is equal to minus eta. Let us take this modulus. Okay, let us don't bother about minus over here, because we are going to define what is eta or what is coefficient of viscosity. We are just going to define that. So eta a dv dx. Okay, now if we want to get eta, then look, this is the force of viscosity, okay, divided by a into dv, sorry, divided by, yeah, a into dv dx. This is what. Now look, if area, this is area, if area is unity, and this gradient, velocity gradient is also becoming unity, then we get the magnitude of the viscous drag or magnitude of the force will be the measure of coefficient of viscosity. So if we define coefficient of viscosity, then we can define in this way that coefficient of viscosity of a liquid is the tangential viscous force, the tangential viscous force to maintain to maintain tangential viscous force acha required to maintain required to maintain a unit velocity gradient, maintain a unit velocity gradient between two layers. I'll read out this once again. Between two layers of unit area. Okay, that means each has unit area, as I have written. A is equal to 1, dv dx is equal to 1, that means velocity gradient 1. So if so, how do we define the viscosity, coefficient of viscosity? So coefficient of viscosity is defined as the viscous force, tangential viscous force required to maintain a unit velocity gradient between two layers, each having area unity. Okay, so that is the definition of coefficient of viscosity. So coefficient of viscosity of a liquid is defined as the tangential viscous force required to maintain a unit velocity gradient between two layers of unit area. Okay, so this is about coefficient of viscosity, about definition. Now question which is being asked in many competitive exam and also board exam, I'll discuss now about this coefficient of viscosity. What is that? The dimension dimension of dimension of eta or coefficient of viscosity. So this is what you have to now find out. So look, we have got eta is equal to f divided by a into dv dx, right? We'll be using this definition. So we know if we want to calculate the dimension of this eta, then we need to know dimension of the force, dimension of the area, and dimension of this velocity gradient. Okay, so this we know ml t to the power minus 2. This you might have learnt already in the class 11, and this area you have L to the power 2 or L square, and dv dx is, see, L t to the power minus 1, and dx is again divided by L. So you get actually here t to the power minus 1. Now look, if we solve it, then we get, see, L will go, 1 L will go up. See, this minus 2 here, you have plus 1, so after addition you will get minus, so ml to the power minus 1 and t to the power minus 1. Okay, this is the dimension of eta. Okay, and it has a unit 1 poise. Okay, it has CGS unit of eta is dyne second per centimeter square. If you go with, so what is the unit now? Unit, you have SI unit. Let us be fixed with the SI unit. So what is SI unit? SI unit is, force is Newton. Okay, then you have area meter square, right? So I'll write n by meter square. This is meter per second per meter, so per second. This is per meter per second, again per meter. So this will be per second. So you get here, you get Newton second per meter square. Newton second per meter square, and this will be called as poise. Okay, a decapoise. No, so this is actually, okay. Let us discuss this poise unit. What is the poise? There is something called decapoise. Okay, so 1 poise is 1 dyne per centimeter square into second per centimeter square. So in CGS unit it is poise. Okay, CGS. So this is actually T means this is second, Newton second per meter square. Similarly in CGS unit it will be dyne second per centimeter square. This is called 1 poise. 1 poise. Poise. Okay, let me write this. So units of eta. So units of eta, 1 poise. In SI unit, it is dyne centimeter per centimeter square into second. This is actually called 1 poise. Okay, and SI unit is called actually Poiseuille. Poiseuille, it is one Poiseuille, Poiseulla, Poiseuille. Okay, one Poiseuille means 1 Newton per meter square. 1 Newton per 1 meter square. Okay, 1 meter square. Now, if you multiply, see 1 Newton. Suppose we know we need to get meter square into second. Then you have to multiply here 1 second. Okay. Meter per second you can multiply. Okay, let me make it more clear. We know that much, but okay, so let us write 1 Newton by 1 meter square into meter by meter per second. Yes, so meter per second. This I'm coming from actually the original definition. Okay, original definition. See, eta is equal to F divided by A into dV dx. Okay, dV dx. This means this meter has come here dx, and this is meter per second, and this is the meter square. So finally, 1 Poiseuille is Newton per meter square into second. This is called 1 Poiseuille. Okay, 1 Poiseuille. So it is in CGS. CGS it is actually 1 poise, and this is in SI unit. This is 1 Poiseuille. This is the unit for coefficient of viscosity in SI unit, and this is the unit for coefficient of viscosity in CGS unit. Okay, 1 poise and 1 Poiseuille. Okay, all right. So it is already 5:20, and my power cut is still persisting. I don't know when again it will stop. Before it stops, I'll stop it here for today. What I'll do, or maybe, madam, can I continue for 5 another minutes, or I'll stop it here for today? Okay, let me stop it here for today. We'll learn the rest of the topic nicely on the next day. So we have Poiseuille's formula and this Stokes law and terminal velocity. Terminal velocity is very important topic, and Stokes law also. Those things we'll learn in a separate class. Okay, I'll stop it here because still the power cut is continuing. It may stop anytime because mobile network, I don't know how long it will continue. Okay, so better I'll stop it here for today. Next day we'll learn about Poiseuille's formula and Stokes law, terminal velocity, and at the same time we'll take up few numerical examples, okay, on this topic. Okay, thank you. Thank you, Deepa. Thank you for your patience.
Thank you, sir.
Bye, Guna madam.